All right, you guys can start.
All right. Like Matt said, we're the Iowa State University Rocketry Engineering Group, and this year we plan on competing in the Space Grant Midwest High-Powered Rocketry Competition. My name is Kyle Gansmer. I'm the lead of the team. We've decided this year to split up the overall team into two different subgroups, one that focuses on the rocket body and the design of the rocket that we plan on making, and another one that focuses on the avionics, the electrical components of this competition. So for the rocket body group, we have Mark Pasalic, Dylan Balmer, myself, Keen Carter, and Emily Cornish. And on the avionics, we have Logan Towers, Ben Sweet, Jason Chapman, Dan Gagnon, and Chris Neiman. And we also have Marn Honest. Oh, sorry, I missed him. Who recently just joined and has not yet been put on a team. So, what does our competition involve?
So the project overview for our competition was to have a rocket, a single-stage rocket with a booster attached that has to reach an apogee and fall safely to the ground. That first phrase is kind of vague, so hopefully I can go into a little bit more detail. The design, or the rocket, is our score is based off of our design, the altitude that's reached, and the documentation of how we build our project. So as far as design and altitude go, we, for maximum points, we need to get the highest altitude. The parachute has to deploy successfully after the booster lets go, and the dart and booster have to separate in a way that is not electrical and doesn't transfer any momentum to the top part of the rocket. And after that, they have to both land safely and without any of the electronics getting ruptured, and we can get some data. The data being recorded is the rotation of our rocket through the air based on the X, Y, and Z axes. And we have a GoPro on board that will be used to correlate the data recorded by our electronics with the actual vision of it. So we'll be graded on that as well.
Space. All right, our project objectives. We decided to go for our design. We decided to go with a carbon fiber body to save on our weight. And we, after doing some quick calculations on what our computer is going to have to look like and our electronics, we decided that we need a 3-inch diameter carbon fiber body to fit everything in there. We need one thing we need to design is our coupler. As Mara said, that can't be electronic. And then we have yet to figure out our fin shape and configuration for that for stable flight.
All these are rough sketches, and we're hoping to improve on that in our research phase.
Okay. Documentation is a scored event in our competition. Thank you. So, all right. Yeah, it's a scored event in our competition, so we'll be making sure that we keep accurate and up-to-date, organized document of all of our work towards the end, the final steps of our project. And we'll need to ensure that all team members remain informed on the current project state.
That includes taking pictures at the end of every meeting to see what we've come up with and hopefully store that all in the same database. In addition to documentation, when it comes to safety, we all planning on doing our safety training so we can work in the lab, owning our own pair of safety glasses. And when it comes to launch day, Kyle already has his level 1 rocketry certification, so he can go up to the launch pad, and I and a few other members of our group plan on getting one this spring.
So this is kind of a visual representation of our timeline so far. So far we're in our research stage of our design, so we're figuring out the basics of what we need to fulfill the requirements for the competition. By the end of November 21st, we hope to finalize that design, and so we can start testing and we can order the materials. We hope to start testing by winter time.
So then for our booster, we had to pick this engine, the Cesaroni 475.
because that is required through the competition. And it is a level 1 engine, so you have to have a level 1 certification, which right now, again, Kyle has. And then the biggest thing is the booster has to detach at the booster apogee and has to drag separate. So that's going to be one of the big design problems we'll have to face because we have to figure out how that booster is going to fall away without imparting any momentum by the body of the rocket.
So on top of the booster, we have our dart, which in our dart, we're going to have a parachute so that it can safely land. And we'll also have our avionics containment unit, which will house all of the electronics that are going to get data. So we plan on setting this on top of our booster. And since it has to drag separate and it can't add momentum, we don't have an engine in this one to keep going up. So it's going on its own. And because of that, there's no charge on this engine that will go right after apogee to release the nose cone and the parachute. So in this, we're going to have black powder charges that you can see at the top, which will go off shortly after apogee, the final apogee. And that will release the nose cone and the parachute so everything will come down safely. And then inside of that, we also have our insulation to protect the parachute and the avionics from getting burned, getting seared. So that way everything's safe for when we do our testing. We can reuse all of this. And at the bottom of our avionics containment unit, we have a spot that will help to make sure that it doesn't fall out, which Dylan will talk about here.
And one thing we ran into when we were trying to figure out how to put our electronics into the cone, into the rocket, was how are we going to put it in there without having to build a new rocket altogether. And so we wanted a design that would be able to easily take out the electronics and put them back in. And so this is what we came up with. We came up with a cylinder type container to put into our rocket. And then on the bottom that has a bolt that goes through the bottom of the rocket with a nut on the bottom of the rocket to keep it tight in there. And what that allows us to do is allows us to easily take out the electronics and put them into a new rocket, or to take the electronics out and see our results. And also allows for when the rocket is falling, that our electronics don't move around and that we can still get accurate data.
All right, so this is a better representation of what our electronics are going to look like overall. Again, they'll be attached to this removable cylinder for easy access and for modification. Our main components are our camera, our Arduino board, which will be used for the control of our electronics and data collection, our IMU, which is going to be our gyroscope sensor, and our battery, which will power the whole thing. This is a representation of one of our potential concepts. We've come up with a few others that are potentially more weight conscious, because the camera, if you put it lower, we can have a lower center of gravity and keep the rocket righted easier. We have yet to decide on exactly what our battery is going to look like. We've weighed a couple options. It's an Arduino, so it doesn't need that much power. So a 9-volt could potentially work.
For the camera required, we're looking to use a GoPro, but if that's expensive, we do have cheaper alternatives.
To go more along with the camera, we have to have it angled down because it's supposed to have a view of the ground at all times so we can see how it rotates as it goes up. And another thing, we do have to be able to see the ground, so we have to have a side panel so we can actually look down, so it'll be at a 45-degree angle towards the ground. We still have to figure out the aerodynamics effects that the window will have on the body of the rocket.
And then back to the battery, we explored our options, and when we discovered that a 9-volt battery might be the lightest and maybe most efficient way to do it, we decided that, and we found a way that it'll power the Arduino and power everything by just connecting it, getting the 9-volt battery, connecting it, and soldering it to a 2.1 millimeter like power plug thing. Yeah, power plug. And then just connecting that to the Arduino, and it should be sufficient enough to power the rocket.
So our group kind of came together a little late in the game. We still just acquired our most recent member today, I think. So we're in the early stages of the design, trying to find the most cost and weight efficient components and just evaluate the best component based on that. We're looking to see, we have our Gantt chart here. Through most of the fall semester, be working on our design and finalizing it. And then early in the spring semester, we'll be moving into the assembly and construction. We do have a goal of completing the construction of our rocket by the end of February, so we can move into the testing phase for that. And the actual competition is at the end of May in Minnesota.
So as far as our budget goes, it's rather rough right about now. We included the entrance fee and travel. As far as travel looks, we went a little bit overestimated because we are at, what was the name of the town? It's somewhere, North Branch, Minnesota is where the competition is, or close to. And the hotels there range from $70 to $200 a night per room. So we're hoping to try and mitigate on that. As far as the GoPro goes, that may or may not have to be paid for, seeing as one of our group members has one. Our parachutes, we may have to change the size. That might lower our costs for a little bit. And the body tube, though we have picked 3 inches in diameter, we have not decided length yet. So the budget is a little bit overestimated right now, but that's better than not having enough money to actually purchase and test a rocket. Is how we looked at it.
So again, for this competition, we had to keep in mind that the design plays a part in our scoring, as well as the altitude, how high it gets, what it reaches. That's also our scoring. Same with documentation. So we're keeping all these in mind as we're going along and trying to, like they said in documentation, we're just trying to keep everything organized, keep it clean, so that way we'll get a really high score in those different categories and hopefully win the competition. We think that our group will help also provide students with hands-on experience with high-powered rocketry, because a lot of them right now don't have it. So we hope that since this competition doesn't require any previous experience, that it can help to give them that experience now. It's kind of an amateur competition. And it'll also provide students, everyone, to get a chance to build their skills, their communication skills, and their skills of working within a team, which is really important in the workforce as we graduate. And we also think that this project is going to be a nice stepping stone to some more advanced projects that M2I offers, like the SciSlab. I'm not sure if you guys have heard of that, but that one's a little more advanced. So we think that this project in the future will be a nice intermediate zone for students to get kind of a feel for what rocketry is like. So that way, if they really do like it, they can advance on to these higher level projects that require more involvement. So with that, is there any questions?